In this video, I want to talk about the vertical line test, which will help determine whether a graph could be a function or could not be a function. And one last thing I wanted to wrap up from the previous example was about the intercepts. Actually, this was from 2 videos ago, but notice that intercepts always have 0 values because when the graph intersects the x or y axis, one of the values has to be 0, because along the x-axis, that always occurs when y is equal to 0, and the intercept along the y-axis always occurs when x is equal to 0. And that's something to notice, is the y-intercept, x must be 0, and the x-intercepts are when y are equal to 0. And another way, if you want to determine, well, how do I figure out the intercepts, like just using the formula without looking at a graph, it would be basically using that idea that the y-intercept is always going to occur when x is 0. So basically, if you plug in 0 into the function, you will get the y-intercept. And the x-intercepts are going to occur when the output, or when the range is 0. And so you can do that by taking your equation and setting it equal to 0, taking your whole function and basically changing f of x, this whole thing, to one big 0. Sorry, you can't see that. And then I would need to figure out the answers to this equation, which, reviewing your intermediate algebra, you could add 2 to both sides and then apply the absolute value equivalency, which absolute value translates to plus or minus 2. And then if I add 1 to both sides, I would have x is equal to 1 plus or minus 2. Which would be 3 and negative 1, right? And yeah, so that would give me those same 2 values, 3 and negative 1, as my x-intercepts. So sorry, I did that a little bit fast. To review, to find the y-intercept, plug in 0 in for the input for x. To find the x-intercepts, plug in 0 on the other side of the equation, set up an equation, and use algebra to find the answer or answers. And also, a lot of times we refer to the term zeros or roots. Those terms for a function always apply to the x-intercept. So x-intercepts are often referred to as the roots of the function or the zeros. The y-intercept, which I said there can only be one, those aren't called zeros or roots. And we'll talk more about that when we get into the chapter on polynomials and advanced theorems of polynomials. So, this actually connects back to what we call the vertical line test. And another question is, why can't we have more than one y-intercept? But if we think about the y-intercept, that's when you plug in 0, what you get as the answer from the function. There can only be one because of that basic property of functions that I mentioned from before, which when you have an input, there has to be only one answer. There can't be more than one answer. So there can only be one y-intercept because when you plug in 0, there's only ever going to be one point. You can't have a secondary point because that would imply there's 2 answers corresponding to the same input. So each value of the input is on the x. There can only be one point for each x value, and there cannot be a second point. And what this leads to is what's called the vertical line test, which is a way of determining whether a graph could be a mathematical function or not. So in your packet here, I've provided some random graphs of various different mathematical equations and relations, and I was, wanted to review using the vertical line test to determine whether these could be functions or not. So looking at the first equation, which is of a parabola, how the vertical line test works is you want to draw a line. Basically, you don't really want to draw the line. You want to imagine in your head these lines. But basically, if you were to draw a line through every point of the graph, a vertical line through every position in the graph, the question you'd ask yourself is, does that line cross the graph more than once? And if the answer is yes, we would say that the graph fails the vertical line test. But in this case, notice that each vertical line only crosses the graph of that equation one time. And if that's the case, we'd say it passes the vertical line test. So to reiterate, crossing more than once is bad. We'd say it fails. If it only crosses once or 0 times, we'd say it passes. So in summary here, we would say that this graph passes the vertical line test. I'm just going to use VLT for a shorthand there, which means that it is a function, that this equation could be written as a function. And another pretty easy way to tell is if a equation is solved for y, like this one is, you can just change y to f of x, and that's a function. And now there are certain instances where that's not quite that simple, but you know, that's another way to tell if an equation could be a function or not. But if you see the graph of an equation, there's a very easy way to determine if that graph is a function. Whereas the graph of a circle, such as this one, based on this equation, we can see that this is not a function, because if we were to draw vertical lines here, we can see that those vertical lines cross the graph in more than one position. And it only takes one vertical line crossing more than once to fail that vertical line test. So you don't have to check anymore. If you see anywhere where the graph is duplicated, that is not a function. So we'd say that this one fails the vertical line test. And so this one is not a function. And also notice that a lot of times if y is within a square, there's certain things that, you know, if that is happening to the y variable, it means it cannot be a function. And yeah. Oh, and again, like to let me try to take a second to say, well, what is the point? Like, what is the vertical line test? Why does it make any sense? But basically, we're checking to see, is there any duplication from the range, from the domain onto the range? Like looking at back to this graph over here, notice that each line kind of finds a point on the curve, like right here, or right here. Where, like, say I'm looking at this point right here, -4 corresponds to 0. -3 corresponds to 3. Those, for each vertical line, there's one point, and that gives me the relationship determined by the original function. And basically, there's no ambiguity towards what point is part of the curve. But if I look at, say, this point on the circle, say, for example, at 3, I have 2 points which are going through 3, right? I have both 1, 2, 3, 4, and -1, -2, -3, -4, -5, -6. I have 2 different points. So if I ask you, well, if the input is 3, what is the output? Is it 4 or is it -6? That's the issue, is there's 2 answers. It's not a single thing. Like in going back to the World Series, we're not allowed to have 2 champions. We're not allowed to have 2 outputs. And the vertical line will find, well, is there duplication? So looking at the last few examples, we can see that a vertical parabola is a function, but a horizontal parabola is not, because again, any curve which doubles back upon itself on the vertical component is not a function. But certain other things, like if you've had trigonometry before, you probably remember the sine or cosine trigonometric functions. Wave functions are indeed functions, because I'm using the term function, but we can see that a lot of types of graphs are functions. Yes, this is a function, but certain things like what this curve, which is called a lemniscate, is not, which looks kind of like the mathematical infinity sign, is not a function, because again, crosses more than one point. And a sawtooth wave, which is a different type of wave than a sine wave, like this one right here, notice that if you're drawing vertical lines, it can appear to pass the vertical line test, but notice that it only takes one position, and in any curve which has vertical component to it, like a sawtooth wave which drops down vertically, is not a function, because again, it would have overlap in certain positions.